Okay, back for sections 5.2. We move on from simple interest to finding compound interest. Again, finance section, a lot of calculator math, and you should have your finance formula chart handy, not heavy, oh my goodness. So here were our simple interest formulas. Over here, we're going to move on and start using our compound interest formulas. All right, when we were finding simple interest, we were looking at interest that is earned only on the original amount. So that present value, that is what we calculate interest on when we are finding simple interest, the original amount. But when you have compound interest, your interest is earned not just on that previous amount, that previous balance or the original amount, but it's also earned on the interest you've already earned. So interest is compounded. Instead of just earn on what you invested, we calculate interest, we put it back in the account, and then the next time we calculate interest, the amount in the account is bigger. So we earn a little more interest, and it stays in the account, and every time we come back around, we earn a little more. So my compound interest formula is a little more complex. We have a lot of the same designations. We've got future value, or the total, is equal to the present value, or my principal, times 1 plus I, where I is my interest rate per period, to the n, and n is the number of compounding periods. Our interest, how do we know if it's simple or compound interest? Well, it's not going to be simple interest if the problem says the word compounded. I always get asked, what are my key words? Well, the word compounded is a key word. All right. So looking at our variables, our future value is the total. Principal and interest. Our present value is that principal, the investment, or the amount you borrow. I is the interest rate per period. Per compounding period. Interest rate per compounding period. So R over M, where M is your compounding period in 1 year. And we're going to talk about that in just a second. So, and then N, this exponent here, N, is the number of compounding periods. So we're going to take M times T. So, for example, this is a good time to put that stuff in. For example, if the problem says that it is compounded semi-annually, that's 2 times per year, twice per year. So the number of compounding periods is going to be 2 times the number of years. Let's say that T is 5 years. In that case, if I'm compounding it twice a year for 5 years, my exponent N here is going to be 10. 2 times 5 is 10. Another one you're going to see will be quarterly. Well, how many quarters are there in a dollar? There's 4. There's also 4 quarters in a year. So again, if T is 5 years of investment, 5 times 4 would give us an exponent there of 20. monthly, if it's compounded monthly, it's 12 times per year. Daily, for this book, remember we assume 365 days a year. My banker's rule would be 360 if it says banker's rule. We're looking at, we even it out to 12 months with 30 days each, which we know is not according to the calendar. It just evens it out so that it's regular. But this book, unless told differently, is going to go with daily as 365. Okay. We're going to find both the future value and the interest earned, rounding to the nearest cent. Well, our formula that we're focused on solves for future value. How are we going to figure out the interest? Well, to solve for future value, we have to know what we start with. And so the future value is going to be what we started with plus interest, which means we can just subtract out what we started with. So we're going to find both of those things. $15,000 is compounded at 3% compounded annually for 19 years. There's my compounded, so I know it's compound interest, so we immediately pull out our compound interest formula and write it down. And then we consider what we know and what we need. 3% is a rate. I, however, in our formula is that rate per period, R per M. Well, my rate is 0.03 when I change it to a decimal. Compounded annually, M is 1 because it's annual. So that is, I is just 0.03 divided by 1 for this case. N is T times M. Well, M is 1, T is going to be 19 years. So 19 is N. Alright, let's plug in what we know. We are taking $15,000 as our present value. 1 plus I, where I is 0.03 over 1, so just 0.03, to the 19 times 1 is just 19. Order of operations, super important here. Start inside your parentheses. 1 plus 0.03 is 1.03. That is what I raised to that exponent 19. And the very last thing I do is going to be to multiply by the present value. That's always my last step. Oh, and sorry guys. Times the present value. There we go. So this is what I end up with in the account. $26,302.59 when I round it to the nearest penny. That's my future value. I was also asked to find interest earned. So to find the interest earned, I say, okay, this is how much I have total. I need to subtract out what I started with. The rest is interest. All right, same 15,000, 3%, same rate, but this time compounded semi-annually. What's going to change here? I is now 0.03 divided by 2 because semi-annually is twice a year. And N is going to be 19 times 2 instead of times 1, so N is going to be 38. So when I set up my problem, it's going to look like this. So because that compounding period changed, those two numbers changed. So inside my parentheses, I'm going to do 0.03 divided by 2 and add that to 1. That's inside my parentheses. That's what gets raised to my exponent, and my exponent is 38. My last step is to multiply it by the 15,000. I did it again. I forgot to hit times because I'm talking. Okay, 0.03 divided by 2 plus 1 to the 38th power, and then multiply that times 15,000. There we go. So now I've got 26,411.97 is my future value. So what happened to the interest? Well, it went up a little bit, right? If I subtract out that 15,000, this time when it's compounded semi-annually, I earned $11,467.65 of interest. So my interest went up a little bit when it's compounded a little more frequently. Let's see what happens if that pattern continues. You're going to notice that the next three problems have the same starting place, but different compounding periods. Compounded quarterly, M is 4. So this time I is going to be 0.03 over 4, and N is 19 times 4, which is 76. So my future value set up. Now notice that I write this down every single time. I expect you to write this down every single time. I want to see the problem written down so that I can see where you're getting your values from. That way, if you make a mistake, I can help to identify where your mistake is made. Did you use the wrong formula? Did you set the problem up incorrectly? Or did you enter it into your calculator incorrectly? Making sure that I did mess this up. I looked at the wrong thing. All right, guys, back to number 2, because I'm looking at an old key. I jumped down to this problem. If I subtract 15,000 here, hopefully you caught me and were yelling at me. This should have been 11,411.97. I apologize. For this one, my future value is 26,467.65, and my interest earned, I got those two mixed together, 476.65. So we're still increasing. I missed a step though. And then finally, no, not finally, we have 2 more. Here we've got monthly. So M is 12 if it's monthly, which means I is that rate divided by 12. N is the number of years times 12, and I can't do 19 times 12 in my head. It's not something I know off the top of my head, so that's 228 as my exponent. So write down your problem so I can see what your values are that you started with. And if you wanted to put 19 times 12 here instead of 228, that's fine. That's not a problem at all. When you compound monthly, your future value, your total principal and interest at the end, comes out to be $26,505.15, which means the interest you earned increased to $11,505.15. So again, the more frequently our compounding period, a little bit more interest. So you can expect that this pattern is going to continue, right? Daily, M is 365 unless we're told differently when it's daily. So I is 0.03 over 365. And N is 19 times 365 because we're compounding daily. So future value, the exponent gets a lot bigger, right? Now, if you're going to write this down as your exponent like this, make sure when you plug it into your calculator that you put your exponent in parentheses. Otherwise, it will take this value, raise it to the 19th power, and then multiply that times 365 instead of raising it to the correct exponent. If you're getting a wrong answer, that's probably where it's going wrong. And you can see it went up a little bit more again this time. Your interest earned is still $11,500. That's $11,523.38. So, what happens to that future value and the interest earned as you compound it more frequently? Well, they both increase because you are looking to recalculate interest on a little bit bigger pile of money each time. If we find the differences in the interest earned as the compounding period increases, we need to look to see is the chain constant, increasing, or decreasing. Okay, so here's what I mean by that. We started out with compounded annually, where M was 1, and then we went to semi-annual, where M was 2, and then we went to quarterly, where M is 4, and then we did monthly, where M is 12, and then finally we did daily, where M was 365. So what was the difference earned in the interest from annual to semi-annual? Well, let's look back at our first page. Interest earned when it was compounded semi-annually was $11,411.97. Interest earned annually was $11,302.59. If I subtract those two amounts, I find that that difference, if it's semi-annually compounded, I earn $109.38 more. What if I compare semi-annual to quarterly? Well, there's my quarterly amount, so I'm going to subtract from that the semi-annual amount, and I can just eyeball that and look and see. It's going to be about $36. Less than 100 for sure, right? No, not 36. Good grief. 56, right? About $56. If you do the subtraction, it comes out to $55.68. The difference between semi-annual and quarterly. So I doubled, when I doubled the compounding period, I got almost $110 more. And then I doubled it again, but this time I only got about half of that, about $55 more. What about the difference between compounded quarterly and monthly? Well, here's monthly, there's quarterly. When you subtract that, you find a difference of $37.50. So you can see that even though the compounding is still increasing, but it's not increasing by as much, is it? What about the difference between monthly and daily compounding? If I look at this, it looks like about $17 or $18. Comes out to be $18.23. So that difference is not constant. The change is decreasing. So this value is decreasing. I'm still getting more as my compounding period increased, but it's not a linear increase. The amount more that I'm getting is not quite as significant. Does that make sense? This is where I hate it that you aren't here to ask me questions in real time. All right, our next page goes to continuous interest. Did you know you can do better than compounded daily? You can have interest that is compounded continuously. If it's compounded continuously, we use an entirely different formula, and the formula is actually a little simpler. You can find that formula right here. Solving for future value, solving for present value. That's my compounded continuously formula. So we've got future value equals present value times e to the RT power. All these values mean the same thing. Rate, time, present value is my investment, my principal, future value is principal plus interest. So you're going to need to use that second function, natural log, on your calculator to find that irrational constant e. So again, we're finding both the future value and the interest earned, rounding to the nearest penny. Same amount, same rate, same term, but now compounded continuously. Compounded continuously means we use our new formula. So future value equals present value times e to the RT. We're solving for future value. We're investing $15,000. My rate is 0.03 and my time in years is 19. So in your calculator, second function, natural log, and notice it opens your parentheses for you. You can do 0.03 times 19 as your exponent, and this is what you multiply by the 15,000. Multiplying by that present value is always the last thing you do. So I get $26,524.01 when I round it to the nearest cent. Right there, round it to the nearest cent, I get a penny. Now, if I compare this to compounded daily, which was 26,523.38, 26,524.01, it's just a little bit more, not a lot more, just a little bit more. Okay, a zero coupon bond. You're going to have problems about zero coupon bonds. A bond is an investment. It's an ordinary corporate or municipal bond usually makes semi-annual simple interest payments to the holders. With this bond, however, there are no interest payments during the life of the bond. Instead, the investor receives a single payment when the bond matures, so those interest payments go back into the bond. The bond matures, you get your original investment, the interest earned that was compounded semi-annually. So that's the thing that you need to remember about a zero coupon bond, is that interest is compounded semi-annually. When it says zero coupon bond, it won't tell you this bit. You've got to know this. You've got to remember this. Find the face value of the zero coupon bond, 30-year bond at 6% sold for $2,546. The face value is going to be what it's worth in future value terms. Sold for $2,546, that's my present value. There's my rate. 30 years is my time. And my compounding period, because it is a zero coupon bond, my compounding period M is 2. Because zero coupon is semi-annual every single time. That's what that term means. So when I set up my formula, I is going to be that rate as a decimal divided by my compounding period. N is going to be the years times the compounding period. So this time N is 60. So I've got future value equals, well, I buy it for $2,546. Got an interest rate of 0.06, compounded semi-annually because it's a zero coupon bond over 30 years. Start on the inside. 1 point something raised to the 60th power, then the very last thing I do is multiply by 2546. So we've got 0.06 divided by 2 plus 1 raised to the 60th power times the purchase price of $2,546. And I see that the face value or the future value of the bond is $15,000 and about 2 cents. Now the thing about calculating these future values of bonds is that we are going to round to the nearest dollar. So you would report that future value, you've bought a $15,000 bond for $2,546. That means that in 30 years you expect to get $15,000 back when you cash in the bond. Alright, let's do effective rate. Effective rate, this R sub E is another symbol, R sub E is another symbol for effective rate. Another thing to call effective rate is annual percentage yield, or APY. You probably seen that term APY when you look at loan information, if you pay any attention to the news or financial information. Alright, the effective rate, or the APY, is the simple interest rate that's basically the same as a compound interest rate. So the simple interest rate that would produce the same amount of interest in 1 year as the nominal or stated compound rate. That's my effective rate, or annual percentage yield. What would be the simple interest rate that would produce about the same results in a year? Now the formula for this, APY, or I could do R sub E, usually I will use APY, is 1 plus R over M to the M. Notice that because M is just going to be, it's going to be 1 year, we just use our compounding period here. And we're not multiplying by a principal because it doesn't matter. It's going to be the same for any amount of money. And then I subtract out that original value. So I'm going to do minus 1. So there's my formula to find the APY, or the effective rate. Find the APY corresponding to the nominal rate, the stated rate of 12% compounded monthly. So R is 12%, which becomes 0.12. M, my compounding period, is 12 because it's compounded monthly. So my APY is going to be 1 plus R over M to the M and then minus 1. 0.12 over 12 to the 12th power minus 1. Calculator math again. 0.12 divided by 12 is 0.01 plus 1, because that's what's going on inside my parentheses, raised to the power of 12, and then I subtract out that 1 to get my interest rate. My interest rate is found as a decimal. We're going to round to 2 decimal places as a percentage, so that would be 12.68%. So when the stated rate is 12% compounded monthly, that's about the same thing as a 12.68% simple interest rate. All right, inflation. If inflation had been running at 3.75% per year and a new car costs $23,500, oh, $23,000, you know what? I really wanted that to be $23,500, but we'll change it. $23,000 today. What would it have cost 3 years ago? We're going to round to the nearest dollar. Okay, let's pay attention. So inflation is running at 3.75%. A new car costs this much today. What would it have been 3 years ago? Well, here's where my FV and PV gets a little confusing. If we're interested in 3 years ago, that would be my previous value, right? Or present value. $23,000 today is the end. So this is what I started with. This is the amount at the end. So the total. You kind of have to wrap your head around that, moving the things in the right direction to get them labeled. We've got our rate here. It doesn't say... doesn't say anything about our compounding period, does it? So we're just going to use 1. Alright, so let's set it up. Since we know we're solving for present value, we're going to go ahead and use this formula, which is basically just this formula rearranged already for us. So PV equals FV over 1 plus I to the nth power, where my future value is that 23,000, and we want to know what it started out as. So we've got 1 plus 0.0375 3 years ago. And inflation is annual inflation. There you go, per year. Oh my goodness, M is per year. I'm having a hard time today, guys. I apologize. So all of the interesting bits are going on in our denominator. I'm going to go ahead and calculate the denominator. 1.0375 to the 3rd power. And then I'm going to divide numerator divided by denominator. So 23,000. There I go again with that extra 0. 23,000 divided by, in second answer to bring up my denominator that I calculated. And I get a value of $20,595.08. Does that make sense? Inflation is positive. That means things are getting more expensive. Now the new car would cost $23,000. 3 years ago, it would cost less. So yes, that makes sense. All right. Last question on this guided notes. Wen wants to have $20,000 available in 5 years for a down payment on a house. They've inherited $16,000. They want to know how much of that they need to invest now so that they'll have the down payment they want and how much they can spend. So they are solving for present value. How much do they need to invest now if they want a certain future value? So present value is what they want to know. How much do they need to invest to end up with a future value that they know that they are interested in having? So they want $20,000 available in the future. 5 years, that's T. This inherited $16,000 just means hopefully it's going to be less than their inheritance, right? That's not going to actually end up as part of our calculation. How much of that inheritance needs to be invested now to accumulate this $20,000 down payment if they can get an interest rate, there's R, compounded quarterly, there's M, and we've got 5 years as T. So my I is that rate divided by M, the number of compounding periods. My rate is 5.5%, so 0.055. M, my compounded periods, is 4, because it's quarterly. N is going to be those 4 compounding periods a year for 5 years. So my exponent is 20. All right, we want to end up with $20,000 at the end of 5 years. I is going to be 0.055 over 4, and my exponent is 4 times 5, or 20. When you plug that into your calculator, make sure you follow order of operations. You should end up with, and we're going to round this to the nearest dollar. So you should end up with, well, if you round to the nearest penny, because that's what I did first, I got $15,219.93, which rounds to $15,220. So they need to invest almost all of their inheritance. They've got $780 they can play with if they want to make sure they're going to have that down payment in 5 years.